Hello, IME 146 students. My name is Treon Giorgio, and I'm going to take you through your IME 146 virtual lab presentations for the quarter. Just like last quarter, we're going to have weekly lab presentations that pertain to what we're doing in lab, and then you're going to do a little assignment that kind of reiterates what I talked about during our weekly virtual lab presentation. So this week, I'm going to kind of introduce the class a little bit. I know your lab instructors did that in class. And I'm going to go through the allowance and clearance calculations with you. But let's first look at our syllabus for the course. Let me go share that real quick. Here we go. So you'll see we have 10 different sections of IME 146 this quarter, and all the sections are going to have one Canvas website, just like we had in last quarter. So if you go on to Canvas, let me jump over to that one. Here and go there. So you can see your Canvas websites right here. If you were to go to your modules and to your course syllabi, you're going to see that all of the different sections syllabi are loaded right there. So what I'm going to show you real quick is an example of my syllabus, which we'll talk pretty much the same syllabus for all the different sections. But you'll see here, once you grab your course's syllabus, you'll see your meeting time, and then the prereqs, the co-reqs, and your lab instructor's office hours. If you have any questions about the course, definitely stop by your lab instructor's office hours. I'm not going to go through the learning objectives. The lab instructors will do that with you. But I did want to talk a little bit about the schedule, because that's why we're here, is we're going to be having weekly virtual lab presentations. So let's look at that schedule real quick. For example, week number 1, we're going to be doing basically mechanical design tolerances. We're going to learn how to assign tolerances for specific types of fits. We're going to talk about that here in a little bit. Then in week 2, we're going to do CNC milling. So you're going to learn a lot more about CAD/CAM programming and the difference between 2.5-axis and 3-axis CNC mill programming. We'll do a little bit of a CAD/CAM demo, and you'll get a lot better at understanding how the process of CAD/CAM programming works within machining. Then in week 3 of this class, we're going to get into injection molding. So we're actually going to machine some aluminum molds and injection mold basically a handle for this Geneva wheel assembly that we're going to be creating. So if you look, we're actually creating 2 different projects in this class. We're creating an air motor towards the end of the quarter and a Geneva wheel at the beginning of the quarter. Now this Geneva wheel, let me stop sharing real quick, is basically a project where you're going to produce a different part every week and learn a little bit about geometric dimensioning and tolerancing at the same time. So there's different GD&T callouts on all the different parts right here, and you'll basically you'll be presented with a drawing. You'll then make the part in lab and inspect the part to make sure it passes all of the conventional and GD&T specifications that were on the drawing. But this is going to be your first part, or your first assembly. It's a Geneva wheel, where it takes continuous motion and it converts it into incremental motion. So you'll be producing this CNC machined wheel right here in week number 2. In week number 3, you'll be producing this injection molded handle. And that leads me right back to the syllabus. Let me pop back there real quick. So in week 2, you'll be making this injection molded handle. Then in week 3, you'll learn about laser cutting, and we'll be making a laser cut Geneva wheel, the green cast acrylic piece. And maybe if we can get enough material, these stands for the Geneva wheel right here. So we'll learn about laser cutting and all the non-traditional machining processes during week number 4. Then week number 5, we'll be doing some water jet cutting. So we'll water jet cut the base and tap it. And then we'll put the part together and learn about tolerance stack up and assembly. So that's going to bring us through the first 5 weeks of this quarter, is making this Geneva wheel assembly right here. The last half of the quarter, the second 5 weeks, we're going to make air motors. These are fully functional air motors, where you're going to learn about, if you look in week 6, you're going to learn about abrasive machining processes. We're going to cylindrical grind or centerless grind the pistons for the air motor. You're going to learn about, in week 7, you're going to learn about basically routings and paperwork. You're going to end up doing you're going to put together all the manufacturing routings and the operation sheets for the air motor and do a little bit of a cost analysis on that. And then weeks 8, 9, and 10 are pretty much air motor production right there. Now, I know a couple of the labs only meet 9 times. So just to let you know, the 9th week is kind of the makeup lab week. Not makeup lab, but it's the extra lab week, where if you have 10 labs, it's kind of a slower lab, and we'll put together air motors during the week 9. And then week 10, we all come back for a final exam for the first hour in lab. So that's going to be the way the course works. I wanted to share the syllabus with you. Now, looking at it, we have lab participations worth 20%. So just by showing up, you get 20% of your grade. There are no makeup lab sessions. If you're sick or something like that, contact your instructor before the lab starts. We have virtual labs for you to make up if you have a school-related absence there. So definitely make sure you get all your participation points. The final exam is worth 30% of your grade. And then the homework assignments and in-lab assignments are worth 50% of your grade. And pretty much all the homework assignments are going to lead into the final exam questions. And we'll do a good final exam review when we get to that point. But that's going to be the class in general here. So let me show you real quick. Stop sharing. I'd like to just show you on Canvas that if we go to home, Professor Zimmerman and I have been working on putting this Canvas site together for all the different lab sections. But you'll see you have pretty much your weekly modules right here. So week number 1, if I was to click on that, you're going to see we have week number 1 where the course syllabus is here, the lab manual. By the way, the lab manual is going to be 100% virtual this quarter. It's not in the bookstore. I know a couple of the syllabi said that you can get a copy of it in the bookstore. Just download it right here and use the PDF version of the lab manual. If you have to have a hard copy, print that PDF if you get a chance to do that. Now, you'll see the virtual lab presentations. They'll show up right here. So when I'm done with this presentation, it'll actually show up right underneath this lecture number 1. And then every week, you're going to have an in-lab assignment that pertains to the virtual lectures and what you're doing in lab. You'll have 1 week to do the assignment. And you'll see the drawing interpretations. That's going to be your first one for this week. And then you'll have one for the next week and the week after that. So just make sure that you keep up with all of the assignments and watching these videos. You might be able to watch them at 1.5 or 2 times speed. However, I do talk fast. So that's going to be the Canvas site. Just wanted to point that out. Turn that off quick. Let's get into the lecture now. So let's start with the material. So this class was designed to show you a little bit more about advanced or non-traditional machining processes. Hence, we're going to be doing some injection molding. We're going to be doing some laser cutting, some water jet cutting. We're going to do some 3-axis CNC machining and so forth. And it's really about putting parts together now in assemblies. So you saw that we're producing these 2 projects. Let me go to full screen view. So we're going to be producing that Geneva wheel and the air motor, like you see right there. And that Geneva wheel has a couple of different types of fits in it in order to make it function appropriately. Same with the air motor there. So we're going to learn about the different types of fits and how tolerancing and interchangeability works this week in lab. And then we're going to figure out all the different allowance and clearance values in our assembly for homework. And we're going to come back next week and start machining parts. So week 1's more of a little bit of design analysis for assemblies here. So in order for things to be interchangeable, in order for mass production to happen, you have to have tolerances. So we've learned, hopefully in IME 145, that once you specify a dimension, when you go try to manufacture it to that dimension, it's really hard to hit the same dimension over and over every single time. So we have tolerances as engineers. So the tolerance is really just the amount of variation that's permitted for that piece or that feature in the design. Now, tolerances will vary based on the function of the part out there. So we want these sizes to be controlled by limits because it's impossible to manufacture parts without some variation. You've learned that. And we have to be able to control those sizes so we can put things together and have it work properly. So in order for the design to work properly, we have to choose a tolerance for it. Now, we don't want to choose a tolerance that's unnecessarily accurate because it's going to be very expensive to manufacture. The tighter the tolerance, the more expensive it is to make. And we don't want it excessively inaccurate because when we go to put something together, it might not actually fit together after after we manufactured the two parts because the tolerances didn't match correctly and it's not going to do its perfect function. So when you're choosing a tolerance for a particular application, really design intent, the end use of the part is number one. What's it going to do in service? And how are those tolerances going to affect the actual design and its function? Number two is a really important one is cost. Cost is definitely important for choosing tolerance. You wouldn't, if you're going to be producing a low-cost product, you don't want to go ahead and have to have a lot of high tolerance features on the part. It's going to be very expensive to produce. You might not be able to sell it for the low cost that you've intended to do. I think you understand that one at this point. Then also how we're going to manufacture it. If we're only limited to having a hacksaw to chop our material up, I'm probably not going to be able to achieve plus or minus 5. I know I'm not going to be able to achieve plus or minus 5 thou if I only have a hacksaw to chop up my material, as opposed to like a cold saw, which I could, with some special precautions and fixturing, I could get plus or minus 5 thou off of a cold saw if I really had to. Then also experience over time will lead you to just assigning tolerances to different features on parts there. Now, once you assign the tolerance, you have another part that it fits together with. And parts really can only fit together 3 different ways. You can have an interference fit, a transition fit, or a clearance fit. So if you think about it, in an interference fit, part number 1, like the shaft, is always larger than the hole. So these are called press fits. In fact, we have a press fit in our Geneva wheel design right up here. This pin gets press fit into this disc, into this CNC machine disc, in order to act as a little drive pin for the Geneva assembly as it rotates around. So we have basically an interference fit in the Geneva wheel right there. You're going to calculate how much later on for homework. Now, the second type of fit is a clearance fit. Part 1 will always fit into part 2 with clearance between the 2 parts. So for an example of a clearance fit, when we have the shaft, we have a shoulder bolt in here holding the wheel on the actual base. There's a clearance fit axially and radially that allows it to rotate and it allows it to shift up and down ever so slightly. So if I didn't have a clearance fit between the shaft and the actual Geneva drive wheel, I wouldn't be able to rotate it right there. So part 1 will always fit into part 2. The shaft is always smaller than the hole in the clearance fit. Now, sometimes, like in fixtures and locating things, you have a transition fit. What that means is the shaft may be larger than the hole, it might be smaller. It depends on which one you pull out of the box of parts. Now, with a transition fit, with these, sometimes you'll heat up the shaft and you'll you'll freeze the shaft and you'll heat up the hole in order to have it one grow and one shrink, put them together. Then when they come to room temperature, they're almost the exact same size and they have a really good fit together. So sometimes some designs on fixtures or transmission, locating features, locating dowel pins, they'll have transition fits out there. But the 2 main types are really the clearance and the interference fits. Now, all 3 are types of fits though. So now, in order to get to those types of fits, we have to have a tolerance on the dimension there. So there's really 3 main tolerance methods on engineering drawings. Hopefully you learned that in your 129 or 130 class at some point. So we have the limits dimensions, we have the plus or minus tolerances, and then we have the block tolerances. But no matter what type of tolerance you have, your dimension, your nominal dimension must match the amount of decimal places your tolerance has. So what I'm getting at, if it's plus or minus 15 thou, you have to have 2.000, 3 decimal places if you have a 3 decimal place tolerance. All right. So the first type of dimension out there that you're going to see in the shop on the drawings is a limits dimension. These give you the maximum and the least amount of material that the feature can have in order for it to be good. So it gives you least material and maximum material condition right there. So the limits dimension. I don't know the nominal value. I assume it's right in the middle, but I've got the limits, so I know if the part's good or bad right there. The next one we've got here is the plus minus tolerance. The plus minus tolerance is basically gives you the nominal dimension, and then it gives you a plus and then a minus value. For example, there's equal bilateral where it goes up and down the same amount. There's unequal bilateral, like you'll see right here on this 257 dimension, plus 3 thou minus 2 thou. So that's unequal bilateral, goes both ways. And there's sometimes unilateral tolerances, which will be plus 0 or minus 0. It goes one way. So it either goes up or down. It's just unilateral. Now, if you don't see a dimension on a tolerance, or if you don't see a tolerance directly on a dimension, it's going to be in the title block. You look in the title block, and there's generally a blanket tolerance that's covered by that covers any dimension that doesn't have a specific tolerance on it. So if it's not a limits dimension, or if it's not one where you have the plus minus values directly on the dimension, like this 257 right there, then you look in the title block, and the title block gives you what the tolerance will be. For example, on this example here, it's point XXX is plus or minus 5 thou. So 3 decimal place ones are all plus or minus 5 thou. And you learned about this in IME 145. This should be a review right here for you. Now, we're going to talk about a couple of definitions. Then we're going to take it one step further and learn how to calculate the allowances and clearances between parts. So limits are going to be the maximum and minimum size the part's allowed to be. The basic size are the target dimensions, which you'd make your SolidWorks model to, or your CAD model to. It's the perfect size that you would have. Then the tolerance is the amount that basic size is allowed to vary. Now, when I have a feature, it's got a material condition. Now, if it's an external feature, its material conditions are opposite of whether then it's an internal feature. So shafts and holes have different values for the material conditions. So when you have the maximum amount of material on a part, when you have a shaft, it's the largest size. So for external features, maximum amount of material is its largest size. However, when you have a hole or an internal feature, the maximum amount of material is its smallest size. So a hole's maximum material condition would be the smallest diameter. A shaft's maximum material condition would be its largest diameter. Now, when we have the opposite of that, the least amount of material, the LMC condition, on the shaft, it's the smallest diameter, the smallest size. On the hole, it's the largest diameter, the largest size. I like to think of material conditions as when they're the maximum material condition, the part is the heaviest. Largest shaft, smallest hole, the part is the heaviest. And on the least material condition, when the part is the lightest, you have the smallest shaft and then the biggest hole. So that's how I think of my material conditions. And we use the material conditions to calculate the type of fit you have between your mating parts. So you can also use your material conditions to figure out the tolerance. So if I have my maximum material condition minus my least material condition, I can figure out what my actual tolerance is. Now, when we have limits of the shaft and the hole, the maximum material condition is the largest size. I mentioned this is just review. The maximum material condition of the hole is the smallest size. The least material condition of the shaft is the smallest size. And then the least material condition of the hole is the largest size. So they're just opposites of each other, whether it's an external feature or an internal feature. Now, when we have parts fitting together, one's always an external feature, one's always an internal when they fit together, when you're just thinking about features. Now, when they fit together, they can fit together 3 different ways, if you remember. They can be a clearance fit, they can be an interference fit or a press fit or a transition fit, either way. So when I calculate the tightest possible fit between parts, I do that at the maximum material condition for the features that are fitting together. That's known as the allowance value. So the allowance is the minimum amount of clearance if you get a positive value from the equation, or a maximum amount of interference if you get a negative value from the equation between the mating parts. So allowance is calculated by doing maximum material condition of the internal feature minus maximum material condition of the external feature. So it's MMC of the hole minus MMC of the shaft gives you your allowance. That'll be the tightest fit between the mating parts. Positive values means there's clearance. Negative values means there's interference, or it's going to be some sort of, it's going to interfere the parts. The parts will interfere with each other. Now, we calculate the loosest fit between mating parts at the least material condition. So if you get a positive value out of this, that's the maximum amount of clearance, or the loosest fit it'll have, or the negative value will give you the minimum amount of interference between those mating parts. So clearance is calculated at LMC, and it's basically internal feature minus external feature. So it's LMC of the hole minus LMC of the shaft gives you your clearance value. And with those allowance and clearance values, I can basically know the fit between my mating parts there, the loosest and tightest fit. So let's try this out together. So for my shaft there, I have 0.51 to 0.47, and my hole, I have 0.50 to 0.49. The limits of the shaft are 0.51 to 0.47, you see that? And then 0.50 to 0.49. The tolerance is 40 thou on the shaft and 10 thou on the hole. Now, when I have my maximum material condition of my shaft, it's 0.51. Then the maximum material condition of the hole is the smallest size, 0.49. Now, when I have the least material condition of the shaft, it's the smallest size, 0.47. And then my hole is 0.50. So check this out. When I do an allowance and clearance calc with them, the allowance will give me the tightest fit. So I take the maximum material condition of basically the hole minus the maximum material condition of the shaft, I get a negative 20 thou. So if I pick those two parts out of the box, they're going to be negative 20 thou. There's interference when I go to put them together. Then I do the clearance calculation, and I get 0.5 is the least material condition of the hole, minus 0.47, which is the least material condition of the shaft. I get 0.03 or 30 thou. I get a positive amount of clearance. There's going to be some clearance fit on some of these parts. So if I have a negative allowance and a positive clearance, what does that mean in terms of fit? Well, that means I have a transition fit if you think about it. Based on the sign of the allowance and clearance calculations values, the type of fit can be determined. So if the allowance is positive and the clearance is positive, we have a clearance fit. They're always going to have room to move within each other. If the transition fit is negative and the transition has a negative allowance and a positive clearance, I have a transition because it's sometimes going to be a press fit, sometimes it's going to be a clearance fit. You can't have a positive and a positive allowance and a negative clearance. That doesn't work. So transition fits are negative allowance and a positive clearance. Then, last but not least, if they're both negative, the allowance calculation and the clearance, it's an interference fit. No matter what, I got to press those parts together. So that's how you determine the type of fits between parts. Now, as mechanical engineers, you're probably wondering, how does this work in real life? Well, there's a bunch of different classes of fits out there. If you look through like the machinery's handbook, there's running and sliding clearance fits, there's transitional clearance fits. So if you looked up what like an RC3 fit would be, it would tell you what type of parts it's made for, and it tells you the allowance and clearance values an RC type of fit should have, or these special transition fits, or these FN1 force fits. So you look up in tables the amount of allowance and clearance a specific type of fit between mating parts needs to have, and you design it that way. So that's why we're learning how to design today for manufacturing, design for subtractive manufacturing, in fact. So that's my spiel on fits. We can also do it this way. So if I looked up in the machinery's handbook and I found that this specific type of fit I need between the block had to have an allowance of 2 thou and a clearance of 10 thou, I could use that to determine what A would need to be on my part right here, the thickness of the keyway. If I knew what parts that I'm getting from my vendor, let's say I'm getting these top blocks from my vendor, I have to make a part now that fits with a allowance and clearance of between 2 and 10 thou. It's gonna be a clearance fit. Key will fit right in there. I have to size A. I know what the size of my slot is with the tolerance of my slot from the manufacturer. I can figure out what A needs to be and what my tolerance needs to be. So let's try it. So I first would calculate A's maximum material condition by using the provided allowance. So what I would do is I would use that allowance equation. And I would put the 2 thou in there. I put the 498 because that's the MMC of the slot. 0.5 minus 2 thou is 498. And I'd end up getting A has to have a 496 maximum material condition. Well, I'm not done yet. I need to know what the least material condition of A needs to be as well. So if you remember, that was 10 thou. And so I take the clearance calculation, LMC of slot minus LMC of key. I put 10 thou in there. I get 502 for the LMC of my slot minus A. A becomes 492. So what I end up with, the target dimension is 496 plus 492 divided by 2. So if I made A 494 plus or minus 2 thou, I would be good to go. And I would have that type of, all my parts would have between 2 thou and 10 thou of clearance when I went to go put these parts together. That's how you design parts that fit together. So hopefully you understand how that works now. So let's try it one more time. So what we're going to do now is we're going to calculate B's maximum material condition. So B is this depth. So B right here is going to be our slot now. And we have our keyway height right here, this 250. The MMC of the key is 251. We have 2 thou there. We get 253 for B's MMC. Then the least material condition would be 10 thou is equal to B minus the 247 because it's 247. You look right here, the 247 would be the least material condition of that slot. So we end up with the 257 for LMC of B. When we add them up, divide by 2, we get 255 for the depth of B. That's what we would want for that target, plus or minus the 2 thou. So that's going to be how we design using allowance and clearance calculations. Now, your lab instructor is going to tell you or teach you a little bit more about it, and you're going to do an in-lab mill block design where you're going to be designing parts like that, and then you're going to be going through the Geneva Wheels assembly drawing packet and answering questions on the fits between the pin and the keyway and so forth, and the material conditions on this actual assembly right there. So I look forward to giving you the virtual lab lectures throughout this quarter. If you have any questions, you can stop by my office hours or any of your lab instructors' office hours. And you have a great day in IME 146. We're going to make some cool things this quarter. Learn by doing. Have a great day.